The motivation of this project stemmed from the fact that most of the individuals participating in the group have played an instrument in the past. Coincidentally, we were introduced to the details of this project right after we had finished covering the chapter on standing waves. After some discussion with Dr. Salas, Julia opted to utilize her flute as the instrument of interest for studying the effects of temperature on pitch. In this experiment, the pitch is defined as the fundamental frequency identified by our brains as a result of vibrating air inside the flute's column. It is correlated with the frequency of vibration, as high-pitched sounds correspond to high frequencies, and the same can be concluded about low-pitched sounds. The speed of sound under constant conditions, which are temperature and humidity, is a fixed value. However, once the properties of the medium are altered, we expect the speed of a sound wave to change accordingly. According to section 15.2 in our class's textbook, it can be said that the speed of sound in air is proportional to the square root of absolute temperature. Therefore, we are hypothesizing that higher air temperatures would induce higher pitches. A total of 3 trials were conducted for the 3 varying temperatures of 303 Kelvin, 297 Kelvin, and 280 Kelvin. To stimulate cold temperatures, Julia placed the flute in the freezer until the temperature read 45 degrees Fahrenheit or 280 Kelvin. To warm up the flute, Julia turned on maximum heat in the car vents and placed the flute in front of them for a total of 10 minutes, until the temperature had read 87 degrees Fahrenheit or 303 Kelvin. For the last trial, she waited until the temperature had dropped to room temperature, which was 75 degrees Fahrenheit or 297 Kelvin. In each trial, she pressed down all of the keys so that the effective length of the air column was measured as the length of the flute itself. However, due to the structure of Julia's flute, the compartment of one of the flute keys split the air column into 2 equal sections. This means that the new effective length would be half the full length of the flute. Furthermore, the wavelength, which is lambda equals 2L, would be the same value for all of the trials. This equation was used to calculate the theoretical frequency in hertz. Given that the wavelength of the standing wave is constant, an increase in the speed of sound would require an increase in frequency. A derivation of this equation was also utilized to confirm the theoretical frequency. In order to calculate the theoretical frequency, the theoretical speed of sound at each of the 3 different temperatures was calculated to solve for frequency. These values were then compared to the observed frequencies produced by the app. The results of our experiment confirm our hypothesis. We observe that a higher temperature in the flute produced a higher pitch,